Yeah. Thanks. Thank you. So basically, the outcome under any scenario, we know what's going to happen. We're going to get this. We're necessarily going to get this index error, and then we can kind of predict. We could catch it or do something with it, and carry along on our way. But let's do some C++ now. Let's see. So I'm just going to do a little main function. I'm going to use, I want to print stuff, and I want to use vector. And what I'm going to do is make a main function. I'm going to make two vectors of cars. One's going to be vec A, and I'm just going to put 10 A characters into it. I'm going to make a second vector. I'm going to put a whole lot more Z's into it. So this one's only going to have A's, and this one's going to only have Z's. And now I'm going to iterate through this by powers of 10. And print out the index that I'm on. Actually, before I do this, let's just print out, can anybody make a guess as what's going to happen if I try to get the 11th element of vec A? Does anybody have any guesses about what's going to happen in C++ if I index out of bounds?
It should throw out too, shouldn't it?
That would be a lovely answer.
That would be a great answer.
But C++ is always out to hurt us. That's the important thing to remember.
Yep. That we're gonna learn how truly conniving C++ is today. So let's compile this and run it and see what happens. So compile. Oh, let's do something at the end so we can tell that it ran. All right, compile this again and run it. Oh, look, everything worked just fine.
Great, run it again, run it again.
All right. Oh, look, everything is still working just fine. And so kind of the point of this is that C++ isn't doing any bounds checking on your accesses.
Can you try something for me, Matthew?
Yep, of course.
Compile it again with -03.
Yep.
Does everyone know what -03 does? So -O is saying you want to do optimizations. -03, so -01 says do only quick optimizations. -02 says, okay, do some slow optimizations too, as long as they're provably correct. -03 says, it's okay to do the ones that aren't provably correct as long as we've never seen them go wrong before. So right. -03 is, let's just throw every optimization at it that we reasonably can.
Yep, and for now we've got the same thing. Yeah. So what's the advantage of C++ not telling us when we're doing dumb stuff? And what does it even mean to index out of bounds of an array? There's no data that we didn't put anything there. What does that even mean? What's the advantage of C++ not yelling at us for doing bad things?
Well, it's faster because it doesn't have to check.
Right. Yep. That's exactly it.
Also, it lets you do dumb things.
I'm not sure that's an advantage, but that's definitely something that happens. Yeah, that's a good point.
Every rare once in a while, you want to do something dumb.
Right. Yeah, and you can sometimes squeak away with it.
But I also realized Juan had the correct answer in the chat.
Yep.
Which is to say undefined behavior. So maybe I missed it.
Exactly. Well, so now we're gonna look and see like what's actually happening when we go out of bounds. So I'm gonna go back to doing this for loop where I start at 1, and then I just increase the index by order of 10. So it'll go 1, 10, 100, 1,000. So we're just gonna index further and further out of bounds until, I don't know, something bad happens. All right, I think
you need
that
to say
should be
which
good.
vector that is.
Oh, good point. Yep. This one. So this should, there's only A's in vector A, so we would really only expect vector A to ever, print out A's. So let's compile it, and we can run it. So, no. So index 1, we see an A. Index 10, there's no data there. It's like zeros. Suddenly, though, now we're seeing these Z's. And where the Z's are coming from is we're actually trespassing into the area of memory where this vector's data are stored. And so it doesn't mean anything like conceptually to index out of bounds on our A vector, but like physically what's happening in memory is that we're actually trespassing onto the raw memory of another vector and like accidentally looking at its data. And then eventually we get far enough out of bounds that we hit this segmentation fault where what the segmentation fault means is like, oh, you're accessing memory that like we know you should never ever access, and that eventually causes the program to crash.
So if any of you want tips on hacking and trying to get other people's information, this is one trick that is very commonly used, where if a program is not being careful about letting the user go out of bounds, that user can sometimes scan memory where they're not supposed to be able to see and actually grab data that they're not supposed to have access to. And on many operating systems, particularly older ones, this was a very common error where that was in the operating system, where someone would be able to get on there and be able to steal someone else's password or other private information by scanning through portions of memory that they weren't actually supposed to have access to.
Right. Yep. And so now so we've seen like, what does it mean to like look at memory that you don't own? But it turns out that if you're not careful, subtly worse things can happen. So we're gonna switch to using arrays for now. We're gonna do an array of 10 characters, and we're gonna fill it with all A's. This will be RA. No. And then we're going to do the same thing. We're going to have a similar setup, except we're going to have arrays instead of vectors for now. We'll go back to doing arrays, and we'll see some fun stuff that happens with that. So this one, I'm going to name this one should change. And I'm going to name this one shouldn't change, or just shouldn't. And I'm going to even make it const so that everybody knows that this definitely should never change. And now we're going to go and print before and after. And then inside of this for loop, we're just going to do some normal iteration now and do it 50 times and just iterate through one by one. And we're going to reset should change. And we're going to set all of the characters to an exclamation mark. So it's starting off as an A, and then we're going to iterate through change 50 characters, even though there's only 10 characters in A, change them to exclamation mark, and then we're going to look at this const array that definitely shouldn't be changing and see what's in there afterwards. This is where you get the realm of really fun bugs. So what we've done here is because we're invoking undefined behavior and working like with memory that like conceptually we shouldn't be able to access, we've actually accidentally corrupted a const section of memory that like from our semantic point of view inside of the program, like if we're trying to debug this, we're like, this is const and it should never be able to change. But when you're debugging C++, you have to kind of also realize that there can be really subtle issues caused by undefined behavior where things that conceptually by definition shouldn't be able to change can change if you're invoking or accidentally doing undefined behavior in your program. And this can cause really, really subtle problems. So we're going to switch from using an array to using a vector. And I think we're just going to do the same thing.
So a vector, you can't specify the type in the template.
Oh, you're right. You're right.
It's also a vector.
I gotta change this. Yep, vector. So this is to go back to being like this, and going like this, and then I think we want to do 10 of these, and it's not a vector, it's a vector, and we'll make this one const again. This one's going to be shouldn't, and it's going to be a lot of these. All right, I think this should be good now. All right, so now we're going to run this, and oh, we got an error. So we got through both of our print statements, but then at the end of the program, we got this double free error. Does anybody have any guesses about what could be going on? Or it's invalid free error. What's inside of a vector? Can anybody tell me like what like in a vector class, like what kind of stuff are we keeping track of?
So I mean, that might actually be a good place to go, is to talk a little bit about what's in a vector, but I bet some of you have some idea.
Right.
An array.
Uh-huh. Yep. And so that array inside of it's variable sized, right? So how is that, like, what actually are we keeping track of inside of the vector?
Size.
So we've got size, yep. And then we've also got, like, where is the data stored inside of the vector class, or is it somewhere else?
So remember that you might start a vector with 10 elements, but then suddenly resize it to have 1,000,000 elements. So how can it possibly fit 1,000,000 elements inside something that was originally declared to have only 10?
A pointer to like the memory.
Yep, exactly. And so the vector has a pointer to a memory somewhere else. And when the destructor gets called on the vector, that memory has to be freed. So like when we're done with the vector and it's pointing to its memory, when it gets destructed, it says, okay, time to free that memory that had been allocated to store my data. So what could be going on here that would be causing issues with the free and the destructor of all things? What we're doing is we're changing a bunch of stuff to exclamation marks.
Maybe writing to memory that was supposed to be const that changed that's not const might
Mhm.
do something with like your freeing.
Yeah. Yep. So you're exactly on the right track. My guess is what's going on here is that we're actually, so inside of that vector, there's a piece of memory where it has the pointer to its allocated data, and we're actually overriding that pointer with just a bunch of exclamation marks. And so when it goes to free the pointer, it goes to an invalid piece of memory and tries to free that instead, because we corrupted like the pointer state of the vector. And so like this type of thing is totally unintuitive. Like if you saw this pop up, and this was maybe not as obvious as the dumb thing that we were doing, and we were seeing like things getting unexpectedly corrupted. If you try to you should always try to debug things from like a logical perspective first, but some bugs in C++ like will make you think your brain is broken because things are changing that should never be able to change. And then you kind of need to take a step back and take a look at undefined behavior.
Well, I mean, or just in general with memory corruption, you can, if you're changing memory that you didn't think you were changing, you can break parts of the code that you don't think you're touching.
You know what
Right.
the worst part about this bug is? That after you do that, it still looks like the vector works fine because it didn't change. Like it shouldn't after it's still an exclamation point. It's still a
Let's see
Z.
this. Yeah.
Which is a little strange.
Which is,
Yeah.
yeah.
Can you run that again?
Yep. I can turn on optimizations too and see if
turn
that,
on optimizations. So turning on optimizations makes, so if you don't have optimizations on, sometimes it does a little bit of extra work that it shouldn't do. And so turning on optimizations will sometimes get to stop that extra work or whatever. But I mean, the interesting part here is that that it could also be optimizations that hide the effect, because it could say, oh, that's const. I know what the answer is going to be. Let's just put the answer in place at compile time.
Right, right. Yeah, I don't know why that is unexpectedly working. That is actually really insidious. Yeah, that's weird. I guess so. The next points that I wanted to make basically are that that having your behavior change based on your optimizer mode is definitely a total calling card of undefined behavior. So I'm going to paste back and go back to a previous state of our program where we just had arrays, one that should change and one that shouldn't. And we're going to do this at 2 optimizer modes. So we're going to do this normally. And we can see that shouldn't got corrupted. But if we do it with O3, and we can see it looks like shouldn't didn't get corrupted. And so if your behavior, your bug is changing when you're moving through optimization modes, that's a total, it's not the only possible explanation, but it's a calling card for like maybe you're dealing with undefined behavior. Or if it changes when you move between compilers, that can also be like a kind of a calling card of doing undefined behavior.
Sadly, merely knowing that you're triggering undefined behavior doesn't always help you track down where it is.
Right.
Matthew's explaining all of this. I will then explain how, if you use empirical, all of these problems go away.
Yeah. And so the very last point that I wanted to make that's kind of interesting is that your compiler basically assumes that you won't do bad things and that you won't do undefined behavior, because a valid C++ program can never do undefined behavior. Therefore, because we'd all know that we're writing valid C++ programs, we can just assume that no chain of execution that would ever lead to undefined behavior would ever occur. And so what we have here is this function, which I've helpfully named bad thing, which takes a Boolean as an argument. And we have this variable. and we're going to set it to be equal to something if this flag is true, and then we're just going to print out our values here. So does anybody have any ideas about if the flag is false, would we have undefined behavior, and if so, why?
Wouldn't val not have a number set for it? If it's
Yep,
false?
exactly. That's exactly it. This is, we've basically reserved space for it, but we haven't actually said what's in that space. And so that basically means, oh, like that doesn't have a defined outcome. And so that's undefined behavior. Yep. And so what's really fun is if we do this in regular mode. Oh, no, I want to do regular mode. So when we called it with the flag being true, then this was, val was set to 42, and we see just like we expect, the flag is true, val is 42. When we called with the flag false, flag was equal to 0, so it was false. And then this is whatever garbage was in that space that we hadn't actually set a value to. But what happens if we compile it in O3? Suddenly, we have the value being 42, even though it was never supposed to be set to be 42, because this is false. So this never should have run, and yet it did run. And what's going on here is that the compiler says, oh, when it's trying to do optimizations, it says, so if this was false, then we would have gotten here and had to have done undefined behavior by looking at this memory that hadn't been set to a value. And a valid C++ program can never do undefined behavior. Therefore, I can deduce that this flag will always be true, and it will helpfully just ignore whatever we pass into this function and do the defined and avoid doing undefined behavior, but do very counterintuitive things from the programmer's point of view. And so that's a super weird and interesting kind of philosophical point of undefined behavior, is because technically it should never occur. The compiler will often do really weird things, kind of counterintuitive around that. And I think that covers all the points that I wanted to make. I guess, does anybody have anything else they want to weigh in with, or questions before we move on to Charles?
I have a question.
Yeah.
So with the optimizing thing, I get how you say it does counterintuitive things because you clearly set this to false, but it still put it as true. So what benefits does optimizing it have?
Oh, sure. So what the benefit of the optimization is, suddenly this can go a lot faster, because if it does optimizations, it can figure out like parts of the code that it will never need, or ways that it can make the actual execution shorter. And so after we compile the code, when we actually run it, it'll go faster. Let me bring up Compiler Explorer, and we can kind of see what happens when we optimize the code. This might work. It's godbolt.org. That's a really good question. Let's do this. And so this is what actually, let's simplify this example. We're just going to do an example where we print out hello. We're going to simplify this example a little bit just to make it more illustrative. So this is what the actual binary code that it gets compiled to without optimizations looks like. And this is all of the atomic computer instructions that we have to execute in order to actually print hello. But if we turn on optimizations, that's sad. That's not what I wanted it to do. Let's see what G++ does. What's supposed to happen in my ideal world is that suddenly we would be doing a lot less stuff, and it would be a really good example. So this is what G++ looks like with optimizations turned on, and then without optimizations, you can see, I guess the Clang didn't produce a very good example for this really simple case, but without optimizations, it's not being as clever in actually coming up with these atomic CPU instructions. It's just kind of doing the straightforward, easy thing. But when we turn on optimizations, it's going to try a bunch of tricks to be more clever to try to get it to go faster.
Okay, I get that. But kind of a piggyback question.
Yep.
Does optimization cut corners that it probably shouldn't, because it does do things that are counterintuitive?
Right. That's another awesome question. So optimization should, if your C++ is perfectly, if you are really careful about not invoking undefined behavior and like doing everything by the book in C++, then turning on optimizations shouldn't affect the actual outcome of your computation. But if you have some of these really subtle issues inside of your code that we were just talking about, and you turn on optimizations, then as you pointed out, it will cut corners and because you're kind of already in the danger zone with your undefined behavior, it will cut corners in a way that can actually cause the behavior to change. And so it's totally possible for a program that isn't written totally by the book to have issues that are caused by optimization cutting corners. But if you are really careful about staying in bounds of doing C++ by the book, then your optimization level shouldn't affect the actual outcome of your computation. It can have other negative downsides, like sometimes what the optimizer does is actually generate more code instead of less code, because it helpfully, instead of doing a bunch of jumps to do a loop over and over again, for example, it might just say, oh, you're going to loop through this 5 times. I'll just put 5 copies of the code inside of the loop into your executable. And so optimization isn't always a good thing, and it can also cause you to take longer to compile. But hopefully, unless you're invoking undefined behavior, it should never cut corners in a way that will cause the actual outcome of your computation to change.
Thank you.
Yeah.
So, Matthew, I'm just trying to reconstruct your example here, because I was going to start from your example. And it's really interesting because I'm using GCC version 9, which is supposed to have much more impressive both error checking and optimizations. And when I try and compile this using GCC 9, it gives me an error with aggressive loop optimization error, where it points out that it has overrun the end of the array right at compile time, because it sees the array, sees that it's going that the loop is going through a fixed number of times, and when it knows at compile time how many times
it'll check it for you.
It's gone through, it can do special optimizations like unrolling loops and whatever. There's all sorts of tricks it can do, and it goes, wait a second, this loop I'm unrolling will cause you to step outside the bounds of this array. It's an error, and it catches it at compile time. That I'm very impressed with.
That's very slick. Let me end my screen share so that you can take over.
Okay.
Okay.
All right, let's see. Share screen. I believe this is the correct one. Share. That looks promising. All right, so this isn't, can everyone see this okay?
Mm-hmm.
Okay. So this isn't I tried to do basically what you were doing with arrays to begin with, where I did the before and the after, and where I do a loop that should stretch past the bounds, because I created array 1 to only have 10 characters. The loop goes through 50 times. And so my expectation, and this is no guarantee, but my expectation was that it would start stepping on array number 2. And when I went to compile it, I compiled it with G++ version 9. The file is just called waves1.cc. I'm using C++ 17. And I did -03, which is the top level optimization. When I hit run, I see all this stuff go by, and it turns out it's a aggressive loop optimization. And it shows me the loop, and it says within this loop, I will go up to 50. And it gives me the warning that writing 50 bytes to a region of size 10 overflows the designation. So it actually catches it and explains what's wrong, which is overflows the destination. I mean, so that's amazing to me.
That's awesome.
That actually works as well as all that. So.
But an error message that explains itself? That's amazing in of itself.
That was supposed to be one of the big things for GCC version 9 is drastically better errors. So that makes me happy to see that sort of thing. I'll note though, if I don't put optimizations, it doesn't try and do that, and it will just compile. The weird thing here is that I don't know if I did something notably different than you, Matthew, but it does not overwrite the bounds of array 2. It does give a segmentation fault afterwards, though, so it's hard to really say what's going on.
Yeah, and I do want to point out, Charles, because I did see that in Matthew's where it said that it had undefined behavior, but it didn't break it down in this example, but not in the other ones. So they've definitely, they're catching it some places, but not others, right? So we can't fall back on that.
So the advantage of an array is that at compile time, it knows how big that array is going to be for sure. When Matthew switched over to a vector, it doesn't do the level of tracking to know how big the vector is going to be. So if we switch all this over to vector, here, let me change all the array stuff to vector, and then we have our two fancy vectors here. Vector 1, we said, is size 10. Vector 2 is size 10,000 or whatever. I believe this should work. Save that, clear, and recompile. Did I not save? I did not save. All right. So with vectors, it doesn't give an error. It just must have written out into space. It doesn't even crash. I bet if I write far enough out, like if I write 5,000 out, I'm betting it'll get far enough where it'll cause an actual problem. Huh.
What happens if you use optimizations for that?
Oh, that better break. Let's find out. Good question. Huh. It just happily writes over whatever. So the problem is there's no guarantee that these two vectors are actually put next to each other, right? And so what is probably going on here is they were put in different parts of memory, and I'm just clobbering some random arbitrary memory. Let's write to a random 500 bytes of space. We'll break something on the computer eventually, right? Wow, and it's just like, oh, sure, let's just keep going. Wow, and that's with optimizations. Whew. Without optimizations doing anything. Okay, so clearly, if we are writing 500,000 spots into a vector that is only 10 spots big, we are doing something we shouldn't be doing. And one of the issues is because it's called undefined behavior, anything could happen, including nothing, right? So let's see what happens if we switch this over. Instead of using the regular vector, what happens if we move over, and I made this parallel to my, or it's in empirical parallel to the source directory. So I can just say, I'm going to use source / tool, actually it should be / source / tools / vec, not, it's not tools, sorry, it's base / vector.h. All right, what this is saying is I want to use the empirical vector instead of the std vector. And here I have to change these two to be emp : vector. All right, the empirical vectors have the same interface as the standard library vector. All right, and what happens if we recompile now? All right, seems to recompile fine. Let's run it. All right, what you'll see is it prints out the before information correctly, and then it says assert error in vector.h line 219, whatever that is, that one of the position is supposed to be less than the vector size, but the position is 10 and the vector size is 10, so 10 is obviously not less than 10, right? So we have a vector of size 10. Indexing into position 10 should be impossible. We can index in positions 0 through 9, but 10 should not be allowed. So the moment we hit 10, it catches that and throws an error. But that doesn't tell us where in our code the problem happened, right? For that, we are going to step into a debugger. All right. Now, first thing of note, in order to use a debugger, when you first compile it, you have to have the -G option. Technically, you don't have to have this option, but what -G does is it says, save all of the actual variable names, right? It means we want to generate all of the symbols that are being used in the code so that we can actually use them in debugging. Is that fair? All right. So we're going to recompile it with the -G option. This will make the debugger give us good information. And then we're going to say LLDB. So I'm using the LLVM debugger. We could be using GDB, which is the GNU debugger. The power of the two is almost identical. The syntax is slightly different. On Macs, LLDB will work out of the box, or if you have the developer tools. GDB requires you to hack your operating system to install it because Apple is very GDB or GNU unfriendly. So hence me just using LLDB and not bothering. On my previous computer, I got GDB to work. It took like a day. I just not going through that again. All right, so I'm going to use LLDB here. And what you do is you type LLDB and the executable name. I just let the executable be called a.l. So I load that. Now we are in the debugger. There are many things you could do in the debugger, but what you typically want to do first is type run. Run runs your code. If there were command line options, if we wanted to do run -x equals 5 or whatever, who knows what command line options you'd want. We don't need any command line options, but if you were going to have command line options, you type run and then the command line options you want to use. So we type run, and I'm actually going to make this a little bit bigger so we can see what's going on. We type run, and we see the code runs like before, right? It prints out what it was supposed to. Then it has the error, and it tells us where the error is. All right. So in a debugger, it gives you the ability to trace where an error is. In LLDB, it's called BT for backtrace. For those of you using GDB, it's just you type the word trace. All right. So again, the functionality is identical. When we type trace, it shows us starting with frame 0 is where it actually crashed. And this is all deep inside of things, right? And we work our way out. Okay, we see that these 3 things are just to make the crash happen. By the time we hit frame 3, we're actually in the vector, because vector is the thing that complained, but really the error is usually in the thing that called vector, which we see is in waves1.cc, which is the file that I wrote, on line 12. All right, if we look here, line 12 is indeed where the problem occurred. Now, one of the things we can do is type frame select 4, because frame 4 is the one we want more information on, so we can select that. I believe, I've been using LLDB for a while. I believe in GDB you just type frame 4. In LLDB you have to say frame select 4. I have no idea why they can't just make these 2 pieces of software more similar, but it is like it is. All right, and so if you type frame select, and because you could step through the different frames, it'll show you the code right around what crashed with a little arrow on the line where the crash happened. All right, and we see indeed, we've selected this frame. We see indeed it's exactly where we thought it was. And here we could even say P for print and pick a variable. So PI, and we'll see that I, right here, when we print I is equal to 10. So we can dig out all of the information what's going wrong from in here. Is this making sense so far? So one of the differences between STD vector and EMP vector is EMP vector gives you the errors like this, right? It tells you, uh-oh, you're going out of bounds, and it tells the very first time you go out of bounds, it catches it and lets you know. All right, so let's quit out of here. Feel free to stop me and ask questions or any of that as questions come up. Okay, just trying to see if I can't see, I don't know why I can't see the chat window while I'm doing all this, but I can. So if anything's important in the chat window, shout at me. Okay, so let's go back up here. We were talking about what the advantage of going into optimization mode is. And one of the things that was pointed out was that it's faster, right? The code you generate is faster in optimization mode. That's great, and that's in general, why would you want to use C++ over languages that do more checks for you automatically? Is because of that efficiency. C++ has incredible efficiency, all right? And that is why you want to learn to use C++, particularly if you're going to be writing things that need every little ounce of efficiency, with the most common things, with the second most common thing being scientific software, and of course the most common thing being games. But where you very frequently need it to be as efficient as possible. And the reason that you don't have all of these checks in C++ is the checks are slow. So you might initially think, all right, well, sure, I'll use this EMP vector, but it's going to slow things down. Well, it turns out what you can do is when you compile, if you compile with -d and debug, all right? So -d says define, and debug means no debugging, okay? If you compile with the ndebug flag defined, so right, you add this to your command line, then what happens is it strips out all of those checks. So if I compile it again with the -d and debug set and I run it, it no longer trips that assert. It no longer sees that there's anything wrong, and you get the full speed. So whenever you need to go back to full speed, you can say, don't do all this debugging. Is that clear? All right. So let's look at our code again. So thus far, we've been focusing on vectors and arrays, and I'll note there's also a source base array.h, which is the same thing as std array. It's just EMP array, and it's a complete exact drop-in replacement, except when you don't have ndebug set, it puts all the extra debugging in to catch all sorts of problems like this. But there's more, and the one that I am most happy with, and by most happy with, I mean it has saved me the most pain, is ptr.h, right? So ptr.h creates an alternative for handling pointers. And as most of you, I'm sure, have become aware of, if you've used C++ for anything complicated, is that pointers are the spot that are most prone to error, and where you really want to work hard to to get them right, and where you can very easily have far worse memory corruption even than what we're talking about with vectors here. So what might we do with pointers? All right, let's go for something really simple. Let's imagine we're going to build an artificial life setup, and we're going to have organisms. So we're going to have an organism struct. I'm going to build this super simple. We're going to have organisms, and what is an organism? It has a value inside. That's all an organism is going to be right now. We'll initialize that value to 0. All right. Well, what we might want to do, I'm gonna delete all of this for now. We might want to say we want a population. So we're going to say emp : vector of organism is a population, right? So we have a bunch of organisms. We're going to call that a population. We'll initialize it to 100 organisms, whatever it's going to be. Now, one of the things that we'll probably want to do when we have a population is we're going to want organisms to be born, and we're going to want organisms to die, right? Because we want an artificial life population. We want all sorts of, and yes, right now we have a really simple organism, but maybe we're going to have much more complex stuff in there in the future. And if organisms are going to be born and organisms are going to die, having just a vector of organisms might not represent that very well. So what we might want to actually have is a vector of pointers to organisms. And I'm not using my PTR class yet. We're going to come back to doing that. And if we have this, we'll probably want to, for example, we have to initialize it. So we'll say for, well, I'll spell everything out rather than using auto. For org in pop, org equals new organism. Okay, this allows us to create a whole population of organisms. Does that make sense? All right, and then we're going to say for size t generation equals 0. Let's say we're going to run it for 1,000 generations. Gen plus plus, right? So we're going to run this for 1,000 generations. And what's going to actually, I'll change this to updates because generations have too many extra meanings. I'm going to keep this. All right. So we're going to run this for 1,000 updates, and every update we're going to pick the organism with the highest value and replicate it. We'll do something, or we could do all sorts of different things. Or maybe we'll pick a random organism. We'll just pick a random organism. How does that sound? I'm making this more complicated than I need to, but random.h. So we have a random.h in empirical. Random. Hey, look, we have a random number generator now. And what we're going to say is we're going to want to replicate an organism. So we're going to pick a parent ID. Parent ID equals random.get uint pop.size, right? So we just grab a random organism to be the parent, and we'll create a new organism. We'll say organism pointer child equals new organism, and it'll be a copy of the parent. So pop at parent ID. All right, and then we'll put the child in the population. Pop, oh wait, we have to figure out where the child should go. So we'll say child will go in a random spot, and then we'll say pop child, oops, ID equals child. Look, it's in the population. All right, and so we'll run through 1,000 births, you know, so 1,000 updates there. And we'll print everything in the population at the end. So we'll do another for organism org in pop. And we'll say std, oops, cout org dot value, and we'll put a space there, and then std. All right, we'll skip a line. All right, we'll skip a line at the beginning too. Actually, we're not printing. All right, so one of the things we're not doing is mutating the child. So we let's also mutate the child, because why not? Child dot value plus whoops, value plus equals random dot get double minus 1.0 to 1.0, right? So that the child will go up or down in value. Now, we're not doing any kind of selection. We could be doing something where we always make sure to take the highest value child or something like this. All right. All right. And there's actually even a slim chance that that I didn't make any mistakes. Let's get rid of the dash D and let's look at that. All right. Let me see what's wrong here. Wow, my computer's going really slow. Expected a semicolon. Oh, sure. I didn't put a semicolon at the end of a struct. No matching. Oh, all right, I don't have. Then we'll say organism. We'll give a default constructor. Give a copy constructor. Oops, this should be. Now there's a better chance of a compile. Now, no matching function call. Ah, okay. That was the problem. So here, when I create the new organism here on line 24, I was passing in a pointer to an organism. I needed to convert that to an actual organism. Getting closer. All right, yeah, because child is a pointer itself, this should have been accessing value via a dereference. Clear before I. Getting closer, okay, and when I print it, same problem. Oh, and forgot an STD. All right. This is now looking good to everyone? All right. How many people think there'll be an error when I try and run it? I don't think there will be, but I'm just wondering if anyone else thinks there will be. And it depends. What I mean is a runtime error, not an error in the underlying source code. Ah, well, I was wrong. Did anyone spot what I did wrong that would cause a segmentation fault? Because personally, I did not. I was planning on there being errors in here, but not yet. And I'm going to actually have it print also the updates. Oops, update. I'm just curious if it breaks immediately or, okay, update 0, it breaks on. So it does make it that far. So I grab a parent ID, but I guarantee the ID is in range. I create a new organism. I access something, but the organism has been created. I adjust the thing I accessed. I grab another organism for the child ID. I put the child in place. Personally, I don't see a problem with any of that.
On line 25, is the parent ID index of pop actually initialized?
Yes, because I created all new organisms here for the entire population.
Okay, yeah.
All right, so what we're going to do is we're going to break out our handy dandy debugger. Sorry, this is taking longer than I intended because I, was going to demonstrate errors, just not these errors. We're going to run it. And bad memory access here. Okay. And so print parent ID. This time I was right at the right point. So parent ID is 16, which should be fine. Print pop.size, which is 100. So we should be indexing in appropriately. Print pop at position 16. It's a null pointer. Well, that's not okay. So, which argues that Emily was correct there. Well, I'm going to show you my pointer class in the field, because this is the sort of thing I use it for all the time. Yeah, I was trying to write a program that worked and then demonstrate that there were other problems with it. We'll get to those other problems, but we're going to start using my PTR class instead. All right, so what that means is everywhere you have a pointer, you instead put it in the template, EMP PTR. And so what this is, now it's still pointers to organisms, but it's using the PTR wrapper. And when you're not in debug mode or, and in the simplest mode, this boils down to simply regular pointers. All right, and so this here, again, all these organism stars, is that it? Yeah. Should be changed to EMP : PTR organism. All right. And then whenever we have an org equals new organism, what we actually want to do is a dot new. All right. Did we have any other news?
Line 25.
Ah, yes. And this is brand new, so we want EMP PTR, new PTR organism, and then pass in the argument. All right. So far, so good for everyone?
Question about line 18.
Yeah.
I feel like this is a stupid question, but is the reason it's not working just because we're not using a reference So like we're just making a new pointer and storing a new organism in it, but we're not putting that back in the vector?
Well, oh, yes. Thank you. All right, now that we found the problem, we didn't need to do this whole conversion. I'm going to leave that off for the moment. Let's just see what we would have had there, all right? But that's absolutely the problem we were having. All right, quit. All right, now the first thing you'll see is if we just compiled using the previous way we were compiling, it does not do the full pointer tracking. And I could jump over to ptr.h. So in ptr.h, it explains that you have to enable emp track mem in order to do the full memory tracking. And the reason that's beyond normal debugging is because that means it tracks every pointer it ever sees and watches everything that happens with that pointer. All right. And so what we need to do is on the command line is -d emp track mem. And now it will do all of that extra work. And I was supposed to use capital D. All right, now when we run it, EMP track mem, pointer tracking is active, excellent. And now it gives us an assert error that we're removing the last reference to an owned pointer, which happens really early on. So the moment we overwrite something, if we didn't have something else dealing with it, it will give us that error. When we go and look where it is, what we'll see is it's this org new up here. And I'm just telling you this rather than showing you in order to speed it up. This org new, we never end up saving it. So the moment it goes away, it complains that we allocated space and then lost track of that space. Does that make sense? All right. And actually, I guess I will quickly show that. LDB, only because we're about to get the same error, but in a different line. And then we run and backtrace. We see that the problem when we get down to waves is on line 18, which is which is up here, because it's this pointer that we lose track of. If, however, we put the ampersand there, like Emily astutely noted, and we recompile, and I'm just going to go straight into the debugger because I know we'll need it, and we run the a.out. What? Oh, run a.out, sorry. We'll see now, it's the error it's giving is now on line 28, right? And the specific error is removing last reference to an owned pointer, but this time it's on line 28. What's happening here on line 28 that we're losing a pointer that we used to have? So this is the line that I was setting up to give the error on. Can anyone spot the problem? I know Emily can see it immediately, but does anyone else see the problem? So we created a new pointer here, right? Child is a brand new allocated memory, and we're saving it in the array. How are we losing anything when we save it in the array?
We're overriding something, aren't we?
Right, we're adding it to the array. Oh, sorry, what did you say, Jamie?
We're overriding something, aren't we?
Overriding something. So there was already a pointer in the array that we did not make sure to delete properly first. So it is pointing out on this line, we are losing memory, right? So it gives us this error, removing last reference to an owned pointer because we're overriding it here. So what we should have done is said pop child ID dot delete. And that's how you delete things, all right? Or delete the MP pointers. So now that it told us where the problem was, we know, okay, we actually did want to lose that. Let's delete it appropriately. Quit, yes. We're gonna compile again with that extra delete in there. And now if we run it, we see we made it almost all the way to the end. All right, or we made it all the way to the end. but at the very, where it actually even prints out all these final values, yay. But at the very end, it gives an assert. Like as the program's ending, it says assert error, right? Removing last reference to an owned pointer. What could that be about? Well, let's jump in there. Run, a.out again. Backtrace, we look in waves, where, okay, now something that was created on line 15, we're losing. Well, 15 was created, oh, so it's part of the pop. So it's like, when we're deallocating this vector, when this vector goes out of scope because the program's done, right? The program's done, a vector will clean up after itself. So when that vector is cleaning up after itself, we're losing a pointer without deleting it. Anyone have an idea of what that could be? So we're deleting anything that gets overridden. What are we not deleting?
What's left at the end?
Remember, we have an entire population left at the end that we never took care of. All right. Now, there's a number of ways that we could track something like this down, because when the program actually ends, it gives us the ID of one of the pointers, right? Removing last reference to owned pointer of ID 1075. Okay, pointer 1075. Where is that? Hard to know, right? Well, let's find out where it was created. So one of the things we can do here, and again, if we go back to pointer.h, this is all in the instructions at the top. We can say to abort when a certain pointer is created. So there's emp abort pointer new. Whoops. And when we compile, if we do -d, emp abort pointer new equals, what was the number, 1075? Is that correct? That'll say when we're creating pointer 1075, abort right there because we want to see what we're failing to delete. We put that in. We run LLDB. And what we see, aborting at creation of pointer ID 1075, we do a backtrace. And we see that's at waves.cc line 25 it was created. Whoops, let's go back to waves.cc. All right, line 25. And indeed, it's one of these children that we never managed to clean up. And that's because at the very end, when we're looping and printing everything out, we don't clean up. And we could just add in pop.delete here. That'll clean it all up. Right? Because it's anything that was left in there that we're printing, we should also be deleting after we print it. Let's no longer abort. We compile.
Would that be pop or org, Charles?
Sorry, what?
That wouldn't be pop, right? Because pop is your vector.
You are absolutely right. It's org. Thank you. This is what my coding also always looks like. It's just like, oh, look, good here. Not something the compiler told me another problem I had. I'm not even going to go through LLDB this time because it should just work. And indeed, it makes it all the way to the end. And at the beginning, and how it said that I was tracking, now when it gets to the end, it says emp track mem, no memory leaks found, 1,100 pointers found, all have been cleaned up fully. And that makes sense, 1,100, right? Because we initially created 100, and then we go through this loop 1,000 times, creating 1,000 more. So we expected 1,100 pointers. Indeed, that's how many it found, and it tells us we've cleaned them all up fully. So this will both tell us, did we create more pointers than we thought we did? And it will tell us at the end if we failed to clean something up. Now that we know it all works, there's no reason for the slowdown that takes, and we would, we could delete all the debugging stuff, and actually we could have even said -d and debug, and now we run it and it runs instantly, whereas before you could at least almost see it go by. All right, I went way over. I'm really sorry that I spent so much time on this. Other things I had planned to show you was just other catches that the pointers make. The pointers, excuse me, the pointers will catch almost any sort of weird error that you have. So so it all depends on what sort of things. But if anything that's not deleted appropriately, it'll catch. Including at the end of the overall execution. So if you try and delete something twice, it'll tell you. If you try and delete something and then access it by casting it or dereferencing it, it'll tell you. If you try and allocate an array, because remember, you can allocate arrays, not just instances. If you allocate an array and don't treat it appropriately like it's an array, it'll warn you. Like if you try and delete it as a normal pointer, but you allocated it like an array, anything that'll cause problems, the PTR class will catch. And when you compile it with -d and debug, it is identical to had you just used raw pointers. So you have the full auditing when you turn on the tracking, but you have the full speed when you turn it off, and it ideally gives you the best of both worlds. Similarly, there's all sorts of other stuff with vectors and arrays I didn't show you. So if you have an iterator in a vector, and then you change the size of the vector so it might have moved, it'll tell you that you're using the iterator in an invalid way. And so we could demonstrate all that, but yeah, I shouldn't. Because I forget what else we were supposed to cover today. Matthew?
We're going to have Emily show off some cool VS Code integrations with GDB and like how to do breakpoints good and stuff.
Do you have time to do a little bit of that, Emily? I'm really sorry.
Yeah, it's really fast. No worries.
Oh, and I should unshare, sorry. Should figure out how to unshare. Stop sharing.
Okay, cool. Can everyone see this?
I can.
Okay, cool. Yeah, so, oh wow, okay. So Zoom is doing this thing where as soon as I share my screen, it like freezes for a bit. So I'm just gonna give it some time and talk for a second.
We can hear you.
Awesome, cool. I can't like move anything on my screen, but I'll be able to soon. Right, so fortunately, Charles already talked about GDB, which is kind of the basis for how the integrated debugging in VS Code works. And so I'm showing this using VS Code, but most IDEs will have some sort of integrated debugging, often based off of GDB or maybe LLDB, but not always. I'm not sure if you're running VS Code on a Mac, whether it just uses LLDB by default. I assume it does.
On a Mac, there only has LLDB, so I hope it does.
Yeah, I assume it's smart about that. Okay, so here I've got just a really simple example program. Can everyone see what the problem with this program is? So the issue is that on line 9 here, we are dereferencing this null pointer. And so if I compile this, wow, okay, my computer's being super laggy. Okay. Yeah, so if I compile this normally, if I just do g++ example.cc and I run it, sure enough, it's gonna say segmentation fault. We know where this error is, but segmentation faults are normally pretty unpleasant in that you don't know when they happened. Of course, if I'd used EMP pointers, we would have a better sense. But either way, we can use GDB to track this down. So like Charles said, in order to use GDB, we need to add the -g flag to tell the compiler to save all of the information that it needs. And so we could run GDB on the command line with something like this, but you already saw that. So instead, I'm going to walk you through doing it visually. Because I don't know, I personally do not ever remember all of the command line instructions for making GDB do exactly what I want via the command line. And I find having a visual interface that's integrated with my code much more intuitive. So in VS Code, there's this convenient built-in debugging tab, which is this little like play button with a bug on it sign. And so if you go here and you haven't yet started debugging a program, it will say, hey, I need some way of knowing how you want me to run this program that you want me to debug. And so it gives you this helpful option to create a file that will basically tell it how to run a program in the debugger. And it's got some pretty intelligent presets. So here it's asking if I want to use C++ or Node. This is in a directory where I've gotten script and stuff, so it can see that I might be using C++ or JavaScript. In this case, this is a C++ file, so I'm going to click that. It's going to ask what compiler I want to use. I'm just going to use Clang, but I could use any of these. And really, I just tested this before and it was fine. Okay, I'm going to use G++, and maybe then it will be happier. Okay, cool. So it automatically just created this and then went to the debugging. But to show you briefly what it did, it created this file called launch.json, which if I go back to my normal terminal, so for those of you who aren't familiar, VS Code creates this hidden directory basically at the root of every project called .vscode. And so if you look in here, this is basically where VS Code stores all of its configuration information. So this file that it just made, sorry, question? Yeah.
I think that was your own voice echoing back weirdly.
Oh, that is strange.
Briefly, it was just at that moment it skipped and then it's
oh, okay, cool. Okay, so right, this launch.json file is basically a configuration file for the debugger that it created and stuck in the .vscode folder. I'm showing you this so that if you ever need to change it, you know how. But actually, it's very good at creating a file like this that will just work. So I don't actually need to tweak any of this. But yeah, in the future, it's good to know that if, for instance, you want to add command line arguments, you do that by adding them into this args array here. If you want to change which program you're running, you can do it here. These are just some variables that VS Code uses internally to like make a smart choice about what to run. Yeah, so this is basically where all of the configuration lives. I'm just going to stop the debugger that it automatically launched so that we can look at it from the start. Okay, so now that I've created this and VS Code is aware of it, it is showing me this debugging panel here. And I'm going to make this a bit bigger so you can see all of it. So at the top, it's got this run button, and it wants me to choose a configuration option. I've only got one option because I've only got one configuration in here. I could have put more configurations, like if there were other files in this project that I wanted to be able to test, and then I would have like a drop-down list of different options. But in this case, I've just got this one. The name is populated from here, so that's useful if you have a lot of them and you want to like not get confused about which one is which. So to run it, I'm just going to click this play button. It's going to start debugging. Okay, right, it doesn't like that I exited it earlier, I think. Oh my gosh, why is it giving me problems now? I like just tested this. Oh, I think maybe it doesn't like that I changed which directory I was in. Okay, so I'm just gonna go back to the directory that contains this file. Okay, trying this again. Fascinating. Okay, so it is not liking, oh, interesting. It's trying to use LLDB. I don't know if I have LLDB. I'm gonna use GDB and give that another try.
And I want to stress for everyone, LLDB and GDB really are equally good. I have not had, the biggest issue I had with LLDB is that every command is different than GDB, so it took me a while to learn the new language, yeah, the new syntax. But other than that, there's, you know, it's the same.
So I made a backup version of launch.json just in case something went horribly wrong during this demo. So I'm just going to revert to that, and hopefully that will fix this. I think it probably got confused by like the fact that I was messing with this beforehand. Okay, cool. This is what it's supposed to do. So you can see I hit play and it started running my file. And it kept going until it hit an exception, which in this case was the seg fault. And so this is doing exactly what GDB was doing before on the command line, except it is showing me on my code where it is. So I don't need to bother with the backtracing and so on. So I can see that it was this line that there was a problem on. I can see the values here of all my local variables. And like if they're more complex objects, they'll have like a drop down where you can see kind of like the members. So iPointer is a pointer and inside it there's like a raw pointer. This is more useful if you've got like a complicated struct or something. This is a very simple program and I don't have like calls to other functions, but if I did, they would show up in this call stack and you'd be able to like step through all of the different levels of complexity or levels of your call stack. So for instance, if I were to, let's see, I want to make sure there's nothing else I wanted to say about this before I demonstrate that. Okay, yeah, so I'm gonna stop that for now. So just as an example, if instead of dereferencing my null pointer in the body of main, I made a function where that happens, and I'm just gonna stick all of that in here for simplicity.
Oh,
yeah. I'm just gonna get rid of that. Okay, and I call bad thing. Okay, and then if I try this again. Okay, so now you can see this call stack has two things on it. So there's main, and if I click on main, it will show me what line in main called the function that I'm actually encountering the error in. And then I can step up into bad thing and see what line on that had the error. And this is really helpful because a lot of times, once you get into more complicated errors and you're using like various libraries and stuff, the thing that causes the error to like originate is buried deep in some library somewhere, and you don't care about that code. But you also like don't care about, oh, there was a line in main where I called this function. And so it helps you figure out like at what level like you should actually be focusing. The other useful thing about this debugger that I just want to quickly demonstrate is breakpoints. So for instance, if I wanted to have this stop running and wait for me to do stuff before it actually hit the seg fault, I could put in a breakpoint. And you can do that by basically clicking kind of on this sidebar here. You can see there's like a little red circle that shows up. So I'm going to click on that, and you can see here in this breakpoints dropdown or menu, it now says I've got a breakpoint set on line 4. So if I want to start over, I can use this restart button on my little debugger controller. It'll start from the beginning, and it will run. And now, instead of hitting that seg fault, it will stop here. And so now I can explore the state of things before the seg fault actually happens. And that can be useful if like, sometimes in the process of like an error triggering, like everything gets destroyed. And so being able to examine the state of your program before that happens is very useful. Just quickly, a couple other things to know. So I've shown the play button, which just kind of continues from where you are until you either hit a breakpoint or an error. I've shown you the stop button, which just stops the program and leaves the debugger. And the restart button, which starts over. The other 3 are also good to know about. So this one is step over. So this will take you to the next line of code at the same scope as your current line. So if I were to click this right now, it would take me to line 5. And so you can use that to like step through your program and watch how your variables change. These 2 change the scope that you're at basically. So step into would be, if I was calling a function on this line, this would go into the scope of that function. And then step out is the opposite, it goes out. So I'm not sure if there's anything on this line I can really step into. I might like end up in the pointer assignment operator. I'm gonna try it. Okay, no, it's not gonna let me step into the pointer assignment operator. But if there was a function on that line, it would let me step inside that function. And here, if I were to step out, it would bring me back up a level, except that it can't because it hits the seg fault. Okay, and the one other feature of this to know about is this watch section. In this case, there aren't really variables that are changing their values, so it's not super useful. But if you stick a variable in here, or it can be even a more complex type of, like, it could be calling a simple function on a variable. I'm not sure like what exactly the thing that determines what it will let you put in there is. I tend to just try stuff and see what works. But so like if I do that, and then I'm just gonna put a breakpoint here after I is created, and I'm gonna restart. So now it'll run to that breakpoint, and you can see anything that we're watching, the current value of will show up here. And here it's not very useful because it's just a variable, so it shows up in variables. But if this were something else, like, you know, if we had a vector and we were looking at its size, that would be useful. Okay, that was a whirlwind tour of using the version of GDB that is integrated into VS Code. Does anyone have any questions?
I'm going to play around with it quite a bit, then I bet I'll have a bunch of questions. But for me, this is very useful because I have not tried debugging anywhere but the command line portion of VS Code.
Charles, you are a madman.
What? I only recently started using an IDE, you know, or a regular IDE. I've been using Emacs for decades. So.
Okay, great. Well, if anyone has questions going forward about integrated debuggers, let me know. The other thing I'm not going to talk about, but I'm just going to mention briefly so you're aware of it, is Clang sanitizers. Google them if you're interested. They're cool. They will pay attention to your code and try and tell you if you're doing bad stuff. They can sometimes catch like you doing bad stuff with memory, although I don't know. I was like playing with some examples for today using them, and like I feel like they don't always catch stuff.
They catch obscure things that are amazing, and then they miss simple things, and it's hard to have too much faith in them. Except if they catch something, it's probably a real something they caught. It's just you can't have faith that they will catch the problem.
Yeah, it's like I don't know, if you're having weird problems and nothing else is working, like you could try Clang sanitizers and they might help.
Sounds good to me. This is all fantastic. Hopefully this was helpful to some of you in terms of just how to think about debugging and that whole side of things. And we are recording this. I think I just managed to get the other recordings to Matthew, and so I don't know if you've put them online yet, Matthew, but he will soon if he hasn't.
They're just up. Hopefully we'll get this video up soon. And next week, we're preliminarily planning on having the enrichment seminar cover some basics of testing, working through how empiricals, native tests work, talking about some exciting new developments from our wonderful D3 team on web testing, and talking about something that has a 3-letter acronym. What's that called, Santiago?
BDD, behavior-driven development.
Yeah, which are like uber advanced, super cool features of the catch testing framework that we're currently not using at all in our tests, and that it would be fun to play around with, and could really make our tests a lot more readable and maintainable.
Awesome. Yeah, I'm looking forward to learning about that too.
We'll also pitch how behavior-driven development isn't actually a super advanced thing and is a way of thinking about coding that you could just do no matter what you're using.
Right.
Cool. Well.
All right.
See everyone on Monday.
Thank you.
Bye.
Thanks.
See y'all. Have a good one.